Right, so from today, we did an example that we carried forward from the other day where we had a missile being launched at a initial velocity of 75 meters per second. Its acceleration is 25 meter per second squared. And the time that would act, 25 seconds. Okay, so from the initial part of this motion, if it was at 53 degrees, what's going to happen is this projectile is going to keep traveling. It's going to go for 25 seconds or so. Then the engine's cut out. So for that first bit of time, we know a couple of things. One, we know that these three values are given, angle of 53 degrees. Two, we know that gravity, although there, is not going to impact this motion because it's already factored into the acceleration vector. So those are all vectors, except for time. So we can go with a velocity calculation for the end. Because at this point, what's going to happen is that projectile is going to fall under the influence of gravity. So it will still have its initial bearing of 53 degrees. However, the velocity is going to be different, obviously, because it's accelerating. And at that point, for this second portion of the motion, gravity is the only accelerating force. So that the engines no longer apply any kind of force to it. So therefore, the final velocity at this point here becomes the initial velocity for this next segment. So if we can find that, projectile motion takes over as we've been doing before, and the trajectory of that projectile will put it some distance downfield. Okay, so from our big four, we can simply find that final velocity vector at this point after 25 seconds. It'll be the 75 meters per second plus 25 meter per second squared times 25 seconds. So this is 625 meters per second. Conveniently, it adds up to 700 meters per second. Excellent. So our final velocity at this point is going to be equal to 700 meters per second, which becomes the initial velocity at that second interval. Well, this problem wants us to find a couple of things. One is the maximum height, the maximum vertical displacement of the projectile, and also the total range. So how far downfield will this thing wind up? Well, I would think that we should do this in chunks. We can find this vertical displacement in the first 25 seconds from the same sets of equations because it's uniform accelerated motion. We do, however, need to take that initial velocity vector. I'll do it up here, I guess. 75 meters per second, and its two components, horizontal and vertical, both velocity and acceleration. So knowing the angle is 53 degrees, first I want to find the y component. So I'm going to find the initial velocity in the y direction. So the initial velocity in the y direction for that first part of the motion is going to be a function of the initial velocity, 75 meters per second, and the sine of 53 degrees. We run that through the calculator, and we get 59.9 meters per second. While I'm at it, I'm going to find the initial velocity in the x. And that's going to be the cosine function this time. So 75 meters per second times the cosine of 53 degrees, and that's going to give me 45.1. Okay, so for the vertical displacement in that first time interval, delta y is going to be VI YT plus 1/2 AT squared, and that's going to be A and the y. Well, it's plus because we're still accelerating. Gravity isn't affecting us, so we are looking purely at accelerated motion due to the rocket's engine. Okay, so if I solve for the delta y then, that's going to be the 59.9 meter per second times our time of motion, 25 seconds, plus 1/2. I need the acceleration in the y direction, so it would be solved in much the same way as we did for the velocity. If the acceleration is 25 meter per second squared, then my y component to that acceleration is going to be 25 meter per second times the sine of 53 degrees. So 25 times sine 53, 19.97. 19.7 meter per second squared. Okay, so 1/2 of 19.7 meters second squared times 25 seconds, all squared. I can work that through. $7,654. 7654 meters, 7.6 kilometers. Okay, I can also find my horizontal distance. That's going to be my velocity in the x direction, 45.1. Times the time, 25 seconds, plus 1/2 the acceleration in the x direction, so that would be 25 cos 53, .0 essentially. Okay, so that's 15.0 meters second squared times my time of 25 seconds squared. I get 5815 meters. Okay, so this distance here is 5815. And this distance here is 7654. All right, all that just to find the first 25 seconds. Now, after that 25-second engine cutout, now we're going to be looking at projectile motion from here all the way over to here. I want to redraw that, just that segment. All right, so from this point at 7654 meters, now we're going to be under the influence of gravity. So we're going to have an initial velocity vector. We said that's 700 meters per second. Yes, we need to break it down into components again. That's what makes this a bit of a beast of a problem, but we can still do it. So the same rules apply. This will be 700 times the cosine of 53. This will be 700 times the sine of 53. X and Y components, so we'll do that. So 559 for the vertical. The horizontal. .3. Okay. Now there's lots of choices, there's lots of ways we can do this. I'm going to solve the time first. Now remember, at this point, we know our vertical displacement is 7654 meters. Okay, which means that the rocket starts at 7654 and it ends at 0. That means the displacement for that interval of motion has gone down. Since that's down, it's negative, negative 7654 meter. That's equal to my delta y. That's my vertical displacement. And remember, we have this function, delta y is VIYT minus 1/2 GT squared. Remember now, gravity is in charge. Therefore, it's going to be affecting the total azimuth, the maximum vertex position it can be because of the function of gravitational acceleration. Okay, we know negative 765.4 meters is VIYT. So there's VIY, 559, times t, minus 4.905 t squared. Well, that's our quadratic equation again. So now I can find the time that it takes to go from here to here simply by solving the quadratic. And I get a time of 126.3. seconds. So now that's going to be the positive root, right? There'd be a negative root, but that makes no sense because that would be actually going back downwards into the ground. So that's for the second part. So the time for the first part was 25 seconds. The time for the second part is 126.3. So now we add the two together to get a total time. And that should be 151.3, sorry, yeah, 151.3 seconds, total time in the air. So that answered part of our question. The other part of our question then is going to be the maximum altitude, or sorry, the maximum range and the maximum altitude. Okay, so our total time is 151.3. The second portion of that motion again was 126.3. So the t, and it's not the half of the motion, but I'm just going to call it the second portion. Still looking for the altitude. Okay, our altitude then can be solved from this equation. Remember, at the apex of this motion here, the final velocity in the y is going to be equal to 0. We knew the initial velocity in the y here, and looking back, that's 559. So look, we know this is 0. We know this is 559. G is a known. That leaves us delta y. Okay, so I solve 0 is equal to 559 minus 2 times 9.81 times delta y. Solving delta y then, I get negative 3.12481 meters squared per second squared. Okay, that's this squared, we bring it over, it's negative. Divide by negative 19.62. And the two negatives go away, so we get a positive displacement, which is always good. Get 15,926.7 meters, okay? So that's this portion from here up. So If this was the 7,000 and change, this additional is going to be 15,926.7, so now we add the two together, 7654 to that. That's the first part of the motion. And I get 23,580, 23,581, say, meters. The source that I got this gave 24,000 meters. Okay, so we're rounding according to significant digits. Okay, so we have the total altitude. Last is going to be the total range. How far horizontally will we go? Well, remember we found the first piece right here. And now the other piece is this. You'll recall that the horizontal component of this velocity, once it's under the influence of gravity, is not going to change. That was 700 cos 53, so that's 421 meter per second horizontal. That's Vx. So our downrange for the second half of the motion, delta x, is going to be Vx times t. We know the second motion's time. The second portion from here to the ground is 126.3. So this is 421 meter per second times 126.3 seconds gives us 53,172.3 meters plus our original 5,815 meters gives us 58,987.3 meters. Okay, our textbook solution that I pulled this one from gives us 60,000, but again, we're doing significant digits. That's about as bad as they get. So I hope that that works well for you.